In this video we will investigate how the geodesic equation of an object moving in space-time can be derived using the variation of its action. It deals with an object that is freely falling and so is not subject to any forces. So an alternative derivation of the geodesic equation involves varying the action and setting this variance to 0. So the action is s and we want delta s set to 0. So we seek the path followed by the particle between the points P at some time tau 1 and Q at some time tau 2, where tau is the proper time measured by the particle as it moves along its trajectory. So that's the proper time measured by a clock that it carries with itself. And we're looking at variation x mu where it undergoes x mu plus delta x mu. So some variation in the coordinates in its path and then setting that variation to 0 to see how to determine the path that the object actually follows. So first we need to come up with an action to describe the particle or object whose path we wish to determine on a space-time manifold. So we have, from the metric here, ds squared is minus c squared d tau squared. And from that we can get the action s is the integral between tau 1 and tau 2 of the Lagrangian, integrated with respect to the proper time tau. And we're looking for something, Lagrangian is the kinetic minus potential energies. We have a free particle here, so we only need to concern ourselves mainly with the kinetic. So we're talking about energy. We need something of the order of energy, and m0, the rest mass times c squared, is the energy of the particle, so it makes sense for a reasonable action. So here we go. D tau can be replaced with this object here, alright, and this is the metric length interval, ds, and we can use that. The minus turns out to be useful later on, and is there, as you'll see later on in the derivation, how that works. Alright, so delta s then will be, let's vary this action, m0 the rest mass and c are constant, the speed of light are constants, so they come outside the integral, and ds is this object here. And for time-like paths we have that ds squared is less than 0, negative, and hence the minus there, and which eventually we will get rid of later on. And hence it's handy to have this minus to start with. So here we go, this object here, we want to take the variation inside the integral here to vary this object inside the integrand. And we want to set that variation to 0, delta s is 0. Alright, so let's have a look at the variation of this integrand part here. So down here we go. Okay, well, here we go, first differentiate the top part, hence we end up with 1/2 times 1 over this object down here. We know from the previous result that ds squared is equal to minus c squared, and we have minus ds squared here, so we get plus c squared there over this object. So variance of this object here over that, and so we get 1/2c times the variation of this object here. Alright, now, so bringing it all out here, here's our integrand again. The variance of the action delta s is this object, rest mass here, minus I over 2 times the integral of this object here. And notice here the minus here and the minus out front here, they cancel out, so that was very convenient, which is why the original negative was chosen in front here. So that cancels out, and we're left with the variance of this object here. So delta s becomes m0 and 2 times the integral of this object here. Now, so we've got to vary each of these items in here, each of these terms, the metric and each of these derivatives. So variation of that. So product rule applies here for each term, or Leibniz rule, whatever you call it, plus this object here. So this variance here, x mu, same over here again. Notice we're using here the delta of dx mu d tau is the same as the derivative, and the delta are interchangeable. So they commute in that way. Variance of the action now is this object times that. Alright. And now this bit here comes from delta of the metric is the partial derivative of the metric with respect to the coordinates times the variance of the coordinate. And so that's how this object here has happened. And then we have, if you notice, two of these objects. this and this are really the same, it's just the indices are labelled differently, so it's really just two of the same object. Hence the 2 there. Alright, now, this second term here, we can express that in a different way, again using the derivative of a product, and then subtracting terms until we end up. So, if we take the derivative with respect to tau of this object here, that means we have to differentiate each of the terms in turn, and then we subtract from it two of the derivatives that result. This whole expression here is exactly the same as this one here, and it will help us later on. This total derivative here will be made to disappear shortly, as you'll see. There we go, next line. So let's substitute in what we have so far, all of this. Okay, and we just notice here that this integral with respect to proper time, this derivative with respect to proper time, when we evaluate that at the endpoints of the path, whatever path this particle is choosing, the endpoints don't vary. And so when we substitute those in, the variation is 0. So this part on the endpoint here, there's no variation, so it will all delta x, this delta x mu at these endpoints here, tau 1 and tau 2, are 0. So this whole term is going to drop out of the integral because there's no variation at the endpoints. Alright, that now leaves us with this object here. Alright, now one of the things we're going to do is next line down, we have this here, like that, delta x mu here, and this derivative of the metric with respect to tau can be broken down into this partial derivative with respect to the coordinates times dx beta d tau times all that object there. Alright, next line down, what we would like to do is instead of delta x alpha and delta x mu, we'd like to have them all the same index, so we'd like to have delta x mu here, and what we can do is the alpha here and here can be swapped to become mu here, and this alpha here can be swapped with the mu's, so this mu and this alpha swap, and this mu and this alpha can swap places, and we end up with delta x mu. Notice how there's alpha here, and mu here, mu there, and they're just labels. We can use any label we want, it really doesn't matter. So we're free to swap them. So this becomes alpha, and this becomes mu and mu. Down here we still have the same objects we had before, delta x mu, but later on you'll see we can take these out. We can factorize these delta x mu terms out. Okay, so next line down we have this object here. Here we go again. Minus this, delta x mu, and here we are. So just rewrite in terms a little bit. Okay, plus this object here. And what happened, you notice there's 2 here and 2 there, and you'll notice that down here they've gone because they've been expanded out, they've been separated out. Next line down. Alright, so here we go, over here, and we're starting to tidy this up a bit more. Here we go, like that. Now, what we're going to do is we're going to collect this partial derivative of the metric, this partial derivative of the metric, this partial derivative of the metric, because in the last couple of lines there has been a little bit of relabeling going on in these indices here, and this gives us this object here. Delta x mu here, delta x mu here. So we're going to factorize that out next line down, take the delta x mu out. And this is looking a bit more like a Christoffel symbol. These last 2 lines here, this object here with the partial derivatives of the metric, starting to look like a Christoffel symbol. The whole thing's set to 0. Now, in this second last line here before the 0, this integrand here, this whole integral here has to be 0. Now delta x mu is the variation, it's entirely arbitrary, so it's not 0. The only way this whole thing can be 0 is if the integrand inside the brackets here is 0. So that implies that integrand is 0, and we're going to do a couple more operations to it to tidy it up. And so here we go, set equal to 0. Now multiply through, rearrange this term, rearranging this, just make it a little bit more pleasant. Now multiply through here by the inverse metric, G superscript mu gamma, contravariant position, 2 indices there, and multiply through. Next line down, the Kronecker delta applies here, the gamma and the nu, and over here this is starting to look like, well, this is a Christoffel symbol of the second kind, isn't it? Times this object here. Now Kronecker delta applies, so a nu is equal to gamma. We get the second derivative of x gamma here with respect to tau times this object here. Now this is just a Christoffel symbol of the second kind, so they can be tidied up to produce this object here. And this is just the geodesic equation again. So once again we've arrived at the same geodesic equation for a freely falling particle in curved space, and that's this object here.